And then, yeah, we could see that it acts as a dipole. And this means the polarization, for instance, are in this case perpendicular to each other. This, let's say, this cut out metallic part of our sheet of aluminium or copper, whatever, it must be a conductor. It's, for instance, shown here. These are the feed points, and here are the feed points in case of the slot. And then you can see here the different distribution of voltage and current. It's clear the current must be very high at the end because this is a short, and this is in opposite to a dipole, means at the end there is no current flow. And so we can build from such idea. Again, it's the Babinet's principle. Babinet is a Frenchman. It's an Eigenname, Babinet's principle. It's like in case of Nyquist. In a lot of colleagues speak it in English. It's Nyquist. It's not correct. It's Nyquist. Okay, then I show you some examples of antennas made from this principle or based on this principle, this Babinet's principle, especially in the image, because this type of antenna is very, very flat. But we also can see that we have other types of such constructions with slots, but not in a sheet. It's for instance, it's slots in waveguides, and then the advantage of very flat behavior, or very flat figure, it's not given in this moment. Also, I showed you some ideas how to make a dipole shorter. Means we make a monopole, but this only works if we have a conductive surface here, like an aluminum plate, or like the outer skin, the outer part of a fuselage of an aircraft. Some examples of application. And now, this was, let's say, the starting point in the last lecture to see what can we do to make an antenna in such a way that we can achieve, let's say, a concentration of the radiated energy in a certain direction. Means the antenna must have a gain, and the antenna should work like a spotlight. We know this from optics. We have a lamp, for instance, a light source, and then we have a mirror with a certain shape, and then we can concentrate the light in a certain direction. And a very simple principle was shown here. This is the so-called Yagi-Uda antenna, and this antenna was first introduced by a Japanese scientist. And if you want to concentrate more energy in a certain direction, then you can realize this with an increased number of the so-called directors. And then the main principle to calculate such an antenna, it's based on, for instance, it's similar, let's say, to the band filter theory. This was another example to increase the gain of an antenna or to concentrate the radiation in a certain direction with very small beam angles. For instance, you can see here, I switch to the laser pointer. You can see here this very large dish for observation of sky, means of incoming radio waves from the atmosphere or from the background of our universe. It has a diameter of more than 10 meters, maybe 20 meters or so, and receives also different frequencies And here in this part, you can see such an antenna with a special dish which is cut. It's not completely symmetrical for a search radar system. It's mechanically steerable, this system. You can see this here on this mechanical parts. And I also showed you some fundamental principles of such reflectors. And a very interesting thing here is the Cassegrain antenna here. It's a double reflector. The feed is here. Radiation goes to the first parabole small reflector. It's in the focal point of this main reflector here, and this concentrates the energy in this direction, in the outgoing direction. Then some examples how to realize such a reflector antenna is very, let's say, very simple methods. Here you can see this double reflector as a feed antenna. You have to admit, or you have to take into account that we speak here about more or less higher frequencies, means 5 gigahertz and higher. This is, let's say, the main application field of such reflector antennas. And another part of such antennas are not the reflector antenna, it's the so-called horn antenna. And I showed you some things here. We have a waveguide as a feed element. All the time we have not discussed about let's say, the basics or the fundamental principles of such a waveguide. It has a completely other mechanism, radiation and wave transportation mechanism in comparison with a TEM waveguide like coaxial line or symmetrical line. This is in this case not important to understand the behavior of this antenna. Here you can see the H-field antenna means in this direction the antenna is wide, it's larger, and here the dimension of the dimension of the feeding waveguide are the same like here. The opposite, we widen this direction of the waveguide, means in the E-field direction, and then we can also achieve a certain gain. You have to take into account that the gain, or let's say the pattern, the radiation diagram, it's very small in this direction, where the antenna has a large dimension, a large measure, and same like here. And the radiation pattern looks like a sheet laying this plane here, very small, and in this direction very small, and here it's very wide, and here is also the opposite, very wide. And now we can combine both antenna types in this pyramidal horn, and then we have a radiation diagram which is small enough in both directions. This is the pyramidal or pyramidal horn, and here you can see the dimensions which you have to know to calculate such an antenna. And then you can see here also the application field for such an antenna is again in the 4 gigahertz range. And this is applied, for instance, in the radar altimeter transceiver antenna. This is not further to discuss. It's only the optimum dimensions to achieve with, let's say, the smallest or the optimum dimensions to achieve the highest gain. This is the background of these curves. Here are some practical realizations of such horn antennas. Pyramidal horn, the same horn as a, let's say, conus. And here it's shortened, very shortened, but then you have to insert here in the front of this horn antenna a so-called lens. It's, let's say, at least dielectric material. It looks like a lens in optics, but with the difference that you cannot look through the lens because the lens must not be free for optical radiation, means for very small wavelengths in the micrometer range. In this case, it depends on the material, what is chosen. It's not, there's no optical feed-through. Yeah, this is another example for such an horn antenna. Here we can see the frequency 5.35 gigahertz, and we can achieve with such an simple construction a gain of nearly 20 dBi. And what is important from my point of view, if you realize such an antenna after calculation, you can directly use this antenna as a so-called gain standard, means what you can measure with this antenna or the radiation which goes out of this antenna, what all comes in, doesn't matter. You can use this as a element which has a defined gain. You can realize such an antenna, let's say, for 20 dBi, calculated exactly, and then it's not necessary to use another antenna for comparison of an, let's say, a second antenna which follows another design principle. Yeah, now we touches the problem of the distribution of the magnitude over, let's say, an area of elements. Reflector antenna cannot have, for instance, such magnitude distribution over the reflector. At the edges of the reflector, it's clear that you can never have the same magnitude like in the middle. You can achieve, for instance, a triangular distribution or cosine or squared cosine or Gaussian. This is also not possible because of this amplitude or magnitude at the edges of a reflector. But you can realize all these distributions if you use, for instance, an array containing or consisting of n elements, single elements. And this is now our new topic, means we will discuss in the next 100 minutes. We will discuss about array antennas, means the antenna consists of a lot of elements, of a lot of single elements. In our case, the elements should be all elements the same, has the same structure, the same behavior. And this is shown here in case of this stacked waveguide. You see here waveguides, one after another, very close together. And the antenna elements are here, it's shown here in this inserted picture or photo. It's consisting of radiating slots. You see here in one waveguide, we have here slot left, right after a certain, let's say, mathematical based arrangement. This distance to the edges and the distance of the slots to each other, and this distance between the slots in this direction, it must be calculated, and it's not possible to make the slots, let's say, after your mood. This must be based on a very specialized mathematical routine. And for feeding this single waveguides with, let's say, X slots, you can realize this with a feeder waveguide, which is perpendicular to this, let's say, radiating waveguides, which consists of an antenna. And you can see this here as a complete arrangement, as a schematic, to understand how it works. In this part of the figure. You can see here the single feed points, and again you can realize this not is in this case here it's a coaxial feed. You can realize the feeding network only with a second waveguide with slots in the other direction. You can imagine I use this waveguide under this bundle of radiating waveguides. And then you can design an antenna which looks like this antenna design here. These are also the single waveguides, every waveguide with the slots you can see here. This is the slots left, right, left, right, left, right, and the antenna is in such a way it is designed that the shape is more or less follows a circle. And so you can achieve with this antenna a certain diagram. But again, this is a new type of antenna because we have here not a Yagi antenna to concentrate the radiation in a certain direction. In this case, we have a so-called array. Means we have elements localized in the same plane, and looking all elements in the same direction means in our main direction, radiation main direction. And here it's written that, for instance, such an antenna you can use as a weather radar antenna, and this type of antenna is steerable, and you can see here some, let's say, mechanical things. Means the antenna is steerable by turning it with mechanical gears and so on. Here you can see some examples of such an array antenna. It's a very large antenna, and the antenna, this area antenna, in this case consists not of slots, it consists of single patch elements. Later on we will see how we can design such so-called patch elements. And for instance, the excitation of this, let's say, radiating patches, it's also realized. You can see it here with waveguide. And where in which type of aircraft such a very, very large antenna from here, from this man or from this tech engineer to this, let's say it's more than 10 meters, this dimension, and in the height it's about 2 meters. Then you can see here the radome, this radome of this Boeing 707. Inside this radome, such a very large antenna is installed, and you can see here that also the antenna it's turnable full 360 degrees, and so the antenna can look around the complete hemisphere where the aircraft is flying. This is a military application, and here we have other examples of such an antenna, steerable of array antennas. In this case, in case of the MiG-35, it's also for a radar system, maybe for weapons, and it's steerable in this case electronically, not mechanically. We also will discuss about how we can steer such an antenna array electronically and not only mechanically. This is done by different phase-driven or different phase differences by the driven elements from one element to the other element. We will see it later. And here you can see a mechanical steered weather radar antenna. You know, weather radar works at about 9.935 gigahertz. and in this case, the mechanical steering it's sufficient for this application. You can steer it up and down and in a certain angle and left and right. Yeah, now this is, let's say, embedded in the complex of antenna arrays. We look to a special type of such single elements. Yet the array consists not only of slot elements, or I mentioned already the patch, and how a patch could be designed, or how a patch looks like. And this is a special type of antennas, which is all very often used in such antenna arrays, because this single element, it's very simple to manufacture, and you can see here the basic principle of such a patch element. You can see we have here a ground plane, a very thin foil of copper, let's say, for instance, 35 micrometer in thickness. Then we have a substrate. It must be a material with a very low loss angle. Means the material must have very, very low losses. You cannot apply, for instance, this we say PVC, what is used for pipes and so on, for installation in the house, for water and such things. What is a very good material? It's the PTFE. We say Teflon. The PTFE is a very good material, but it has very good material regarding the loss angle. But it has a disadvantage. The mechanical strength or the mechanical behavior is not so good. It's not enough. There's not enough stiffness and so on. And so let's say 40 years ago, starting 40 years or 50 years ago, it was starting to use or to develop special materials for such type of antenna, which has very good mechanical behavior and also very good electrical behavior, means very, very low losses. And you can imagine if you have to realize a very large antenna array consisting of a lot of such elements, let's say 24 by 24 elements. It's a very high number of such elements, and they consume a lot of place, and it should be clear that all elements must lay exactly in the same plane, and so this material must have a very high stiffness, must be very stiff, so that there's no bending in the plane and so on, and it's not so easy to realize. Okay, this is only the background for our discussion, which follows now. You can see that the thickness of this dielectric material substrate, it's here given by the thickness T, is normally very, very small in comparison with the wavelengths. 100% of the wavelengths are in this range. And the wavelengths here, it's given in free space wavelength, is clear. And the substrate has a permittivity, means the wavelengths in the substrate, it's smaller than in free space, it's clear. You can divide it by the square root of the permittivity of the relative permittivity. And you can see here in which range, now it's given here, this is the metallic sorry, this is the metallic thickness. And this H here, it's the substrate thickness. And this substrate thickness lays in this region about regarding the free space wavelengths. And here we have a cross section of this patch antenna. Again, here the thickness H. The thickness of the copper or of the conductor material also can be not only copper. Normally, it's used copper. It's used in a very high number of cases, but we can also use other materials. The problem is you have to use such materials which has a good conductivity and which you can, for instance, you can make a structure by etching, by photo etching, and from this point of view, copper is perfect. It has a very high conductivity, and we have, let's say, special materials for etching the structure in this way here. Then the patches can have very different shapes. For instance, we can use a square shape as a patch, then rectangular. Let's say this is the normal case. We can also apply circular elements, and this is another type. It's elliptical elements. Depends on what we want to achieve with these elements, with the single element. Yeah, this was already explained. And what I have to mention is that the microstrip antennas are very useful for aerial vehicles because of the good integrability. It's clear because it's very flat in the surface of the fuselage, also of the wings and the appendages. And they have a high flexibility regarding radiation pattern and polarization. This behavior of an antenna is at least very important for a certain application. Yeah, now we can see here the basic formulas. How can we calculate the dimensions of such an antenna for a certain or for a given frequency, or better, for a given wavelength? Means in every case frequency wavelengths in free space. But the dimensions of the antenna, here we have a circular patch, it's clear, has to follow the rules what happens on the substrate, and means we have not here the free space regarding the dimensions. Here we have to consider the dielectric material with the permittivity, with the relative permittivity epsilon relative. And this is one parameter, and the next parameter is the thickness of the material itself. If you change the thickness and you hold the dimensions, only changing the thickness and holding also the relative permittivity means at least that you change the frequency. It means the resonant frequency of this antenna, or the center frequency of this antenna, only changing the thickness of the substrate. Changing the thickness, changing the relative permeability here, and changing the dimensions. All these three parameters are changing a lot of the behavior of this antenna. It changed, first of all, the center frequency, the working frequency. It changes the gain of the antenna. It changes the bandwidth of the antenna. It changes the let's say the side lobes and so on. At least it influences all the antenna parameters we have to look for. And in this sketch here, we can see another type of feeding. Here in this case, we have a so-called probe feed antenna. Means we have here the coaxial connector on the bottom side of the full metallization. It's in our case named ground plane. Then we have here to etch a small circle out of this metallization. Then the inner connector or inner conductor of the coaxial connector is fed through to the circular microstrip patch element here on the surface. And it's, for instance, here, the inner conductor, it's soldered on the top. It's not visible here. Normally, you had to make here a point, a dot. You can see then this in practice as a solder, a solder point. Without soldering for feeding, you can see here another possibility. It's named a partial coupled feed. Means we come from the side here. This is this broken line strip. It's a so-called microstrip line. It's nothing else than a strip over a ground plane. You see here the ground plane substrate is the same, and here we have no patch, only we have a small strip with a width W, and this width determines the impedance of the strip. And we can choose this. We can choose it in such a way that it's, for instance, 50 ohm in connection with the thickness, with the thickness H of this substrate. And you can see this part. It's the rotating patch, and the microstrip line goes under. This is the ground plane for the patch. Goes under the ground plane, and here in the ground plane means in this plane here, it's etched a rectangular window, and so the strip through the rectangular window, it's coupled to the patch here, what you can see on the surface. This is the radiating patch, and the slot, the rectangular slot, it's etched in the ground plane, and this gray field or this gray rectangular, it's our rotating patch, and this broken line, it's the feeding microstrip line for this patch. It's only a second possibility to make or to transport the electromagnetic energy through this slot to the patch. And then another possibility is the so-called proximity coupled feed. It's very simple. Here you have the ground plane, then you have let's say with a substrate 1, no, let's say what substrate 2 with relative permittivity of 2. Normally we use the same, but yeah, this example shows only that you can use different substrates. And this substrate also carries the microstrip line, like here. And then it's clear that the microstrip line is over the, let's say, H1, thickness 1 over the ground plane. And then we have a second layer, only permittivity, in this case, permittivity 1. And the same like here, then on the top, we have metallization. This is our patch. Maybe the same patch like here, same patch like here, only the excitation of the patch. Here it's done through a window, through a slot in the ground plane. And here we have no slot because the microstrip line directly feeds under the patch and looks up to the patch. Between the patch and this plane, we have only the material of the substrate 1 with the permittivity epsilon relative 1. There's no other metallization between these two substrates. And this is in opposite to this one here. We have here in the middle a ground plane. Downwards we have the microstrip system, and upwards the coupling mechanism with the patch. Here we have some formulas. It's not necessary to discuss this these cases, only for you as a as a guideline if you have some interest to look for such a patch antenna. Maybe there is among your colleagues radio amateur, and yeah, you can also realize a patch antenna, for instance, for very high frequency range 100, we say 2 meter band, or a 70 centimeter band. This or radio amateur bands in Germany for ultra high frequencies or very high frequencies. It's clear that such an patch element, a single antenna, has very large dimensions. Let's say for 70 centimeters, the name says it's 70 centimeters in square, and you can realize this in also with substrate. Air as substrate needs some holding elements from, for instance, dielectric material, or you can use foam as a substrate, like polystyrene foam, and then you can also realize a gain antenna or element, a patch antenna element with a gain of about 6.5 up to 7 dBi in 70 centimeter range for radio amateurs. In our case, we discuss about frequencies much higher, let's say 1 gigahertz or higher, and we use again substrate material with a higher permittivity, let's say 2.7 up to 10. This is the permittivity, and the higher the permittivity, the smaller the patch element. It's clear. Here we have the next problem of feeding. This is of a single element, and here in this examples, the problem is how to realize the feeding in such a way that we can achieve at the input of the. This is also a microstrip line, should have 50 ohm. How can we realize the feeding in such a way that we can achieve immediately a good matching? That means the power coming from the generator, it's going completely in the patch, and there's no reflection. Means we have to realize the feeding at the patch element in such a way that it shows 50 ohm. And this is one possibility. Means in principle, you can say, okay, I come here with the microstrip element and go to the edge of the patch. But if you look from this side, from the generator side, to the edge of the patch, where the feeding connects or contacts the patch, then you have never 50 ohm. It's in principle in the range of several hundred ohms. This impedance, the radiation resistance, you remember, and then you make this recessed. You mean here you have here slots, and the connection is not at the edge; it's inside the patch, and you can achieve this in such a way that you can hear in this plane exactly 50 ohm, and so the complete power coming from the generator is delivered to the patch. It's one possibility. The other possibility is shown here. This is, from a mechanical point of view, not very sensitive. It's it's a good solution for photo etching and so on. Here it's the same, but in this case, maybe the slots are very sensitive. Could be very small. Could be in the range of 25 or 30 micrometers. You can also achieve a good matching, but with a higher sensitivity regarding the mechanical dimensions. Okay, now this is another possibility for feeding with matching. This is here with a line transformer. It lays on the hand, means here we have a very high impedance and we have to transform it down to the 50 ohm, which coming from the generator. This is our microstrip transmission line. Let's say with 50 ohm, because the matching to the generator is given by 50 ohm. And to achieve a matching to this high impedance at the edge of the patch, like here, then we have to insert this force wavelengths line transformer. You can realize this in also with photo etching, but you have to keep in mind also depends on the material of the patch, on the substrate material and so on. In some cases, it can be a very high ohmic here. And so the width of the strip, if you use, for instance, a high permittivity of the substrate material, then the width of the strip also can be very, very small, and you can get conflicts with photo etching. Maybe it can be smaller than 100 micrometer. And so, yeah, it's also sensitive for mechanical processes. Here you can see, for instance, the normalized input resistance for instance, here the recessed microstrip feed line. And it's clear if you are in the middle of the patch, then the excited mode shows in principle short. Yeah, this is shown here. And at the edge of the patch element means here, it's normalized to the input impedance. It's 1. And yeah, you can see here, if you go further means the input resistance, it's going down or it's decreasing until to 0. This is what you can see here from this graph or from this figure. And another possibility to make some things or try things in one, to excite left or right oriented circular polarization, left-handed or right-handed. You can do this in this way here. This is called 90-degree hybrid. It's also an element made from microstrip lines. And here you have the driven edges. And also here you can see this transformer. This transformer together with this point and this point transforms the impedance from the edge to 50 ohm at the output of this hybrid. Only for explanation, the hybrid makes nothing else than a phase shift between this point, this output and this input. The phase shift between these outputs are 90 degree. And if you want to change the rotation direction of the circular polarization, then you have to make the opposite. Then you have to realize the hybrid in such a way that the phase shift it's exactly on the opposite. Means if you have here in this case 0 degree relative and plus 90 degree, then you have to make here a 0 degree and here plus or minus 90 degree. And this it's normally realized with the lengths not here, but the phase difference must be realized exactly here at the feeding points of the square patch. Yes, and you can realize this if you make the line length, the complete line length from here to here difference. The hybrid itself makes or holds the 90 degree over, let's say, a certain bandwidth. This is the reason why we use a hybrid and not only, let's say, a line with a length X or Y. Yeah, what I want to show you here in this example, We have here, for several years ago, realized an antenna array, and you can see here the frequency range is very high. It's in the near of 30 gigahertz. You can see 20.462 gigahertz. Let's say it's about 30 gigahertz in all cases. And the substrate material was chosen as a so-called low temperature co-fired ceramic technology. Means this ceramic has a very high permittivity, and the value is shown here, 7.07. The substrate thickness is very thin, and because of the high frequency, about 30 gigahertz, also the dimensions of the patches, it's a single patch here, it's very, very small. This is a readout of a very primitive program for calculation of such patch elements. You can see here that the element dimensions using this material with this very high permittivity are very small. The patch length, it's because it's given in centimeters, it's 0.182 centimeters, means it's 1.82 millimeters. Yes. The substrate thickness here, because it's given in centimeters, it's 108 micrometers. The loss factor, it's in this case, it's not so very good, but it's good enough. It's 0.002, means 2 exponent minus 3. Then the patch width is a little bit larger, because we have to excite, let's say, a special mode, and it's 1.95 millimeters. Means the patch dimensions are very, very small, and what you can achieve with this design, you can achieve a bandwidth very small, 1.4%. Then we have a directivity in dB. It's not the gain, but in principle you can say it's about a gain. It's 5.5 dB or 5.5 dBi. The input resistance, because of the chosen feeding point, it's should be about 50 ohm. You can see we have not matched it exactly. And the efficiency of the antenna, because of the inner losses, you remember efficiency, it's radiation resistance divided by radiation resistance plus loss resistance. We can achieve only 70, let's say 72%, not 100. And now what I want to show you is the influence of the thickness. We only change here in this, for example, the thickness of the substrate, nothing else, only the thickness. Now we make the thickness larger. Here 108 micrometer, here twice 260 micrometers. What happens? We have to keep the frequency at the same level. Means we have to reduce, because the material is thicker, we have to reduce the patch length. It's now only 1.75 millimeters instead of 1.82. Then the other parameters are the same. The patch width, we also have to correct it to excite a wished mode. And so you can see that the resonance frequencies, we have to keep it at the same level. The bandwidth, you can see here, goes up to 2.6%. You can say about twice bandwidth we can achieve. Directivity level, the same. Resistance, it's clear, the same. But if the efficiency, you can see here, it's more than 10% better. Now we make the thickness of the substrate 3 times larger or 3 times higher in comparison with this first. Keeping the same frequency, means also we have to reduce the dimensions of the patch to keep the frequency. You can see here the width and the length, or sorry, the length and the width. And you can see here what happens. The bandwidth, it's also increasing further in comparison with this value. Now we have 4.3%. Directivity, it's a little bit smaller, but maybe it's a calculation problem. Input resistance, it's hold in the same level. But now look to the efficiency. The efficiency, it's going up to about 95% in the near of 100. It's very good. Now we make the substrate much thicker, 4 times this value. It's now 432 micrometers in thickness. And what we can see, the patch lengths also have to reduce to keep the same frequency, to hold the frequency. Also the patch width we have to reduce, but bandwidth, it's growing up of 7%. Directivity, it's a little bit larger, a little bit smaller. It's like here. And the efficiency, it's growing up to 97%. And this is a very interesting result. And in this slide, I have the same calculations, but in this case, I used, let's say, air as the substrate, permittivity of air, it's or vacuum. But you can see here the substrate thickness is exactly 100 micrometer in the calculation. You can see here what happens. The patch length is much larger. It's clear because the permittivity, it's only 1. Here you can see it here, 1, 1, 1. But the effects, what we can see, at least in comparison, it's that the bandwidth, it's also increasing if we make the patch thicker and thicker. But another effect is if we choose air as a dielectricum or vacuum, then we have a higher bandwidth at the starting point. You can see this also here. And here, in case of twice the thickness, we have 5.3%, 3 times the thickness, we have about 9.3. Also the directivity, 9.6, 9.6, 9.3, 9.2. Means, and here the bandwidth is also much larger in comparison to this patches, which has a very high permittivity here. What is the reason? You can see here that the dimension of the patch elements are much larger, about 4 times larger than in case of this LTCC substrate. Means the so-called radiation area, radiation aperture, it's larger than in case of the LTCC substrate. And this makes, in principle, the directivity larger in comparison with this high permittivity substrate. This is what I want to show. Again, a patch element, if you use a patch element with high permittivity as a substrate, the element could be realized very small, it's clear, but the directivity drops, it's not so high. And also the bandwidth is smaller. Yeah, bandwidth is smaller, and it's clear the dimensions of the patch elements or the measures width and length of the element are also smaller, but you have to pay this with a worse performance of such a patch element. And now in the next slides, we will discuss what happens regarding if we use a single element with more or less good performance in an array consisting of n such elements. Here, it's before we go to the areas here on this in this part. Again, what can we or how can we excite circular polarization? You can use, for instance, a square patch like this with a slot in this direction. And then you have a certain direction in the polarization, in the circular polarization. And you can see here, if we make this, it's only another figure, but you can make here the slot in this direction, then you change the direction of polarization completely in the opposite direction. Assume here it's, let's say, clockwise or right-handed polarization, then in this case it's left-handed polarized, the circular polarization. And here you can also use a square patch, and you can cut the edges here. You cut out the corners in this way, and you have here 2 feed points. Yeah, either if you use this feed point, it's, let's say, left-handed. If you use this feed point, it's right-handed. Normally the feed points are not on the edges because it's high ohmic. You can use the feed points here a little bit more inside if you use this as a single element for circular polarization. But normally, in case of an array, you have to feed this on the edge with a microstrip element here or here. But again, then you have to insert here a transformer to match it to a special wave impedance. Yeah, and another possibility is you can use an elliptical shape of such a patch. You can also achieve circular polarization if you consider the major axis and the minor axis in a certain relation to each other. Yeah, now again, an array of such patches. Here we can see some examples for an H or 2 by 8 element patch. You can 16 elements together. You can see here one possibility to arrange or to feed such an array. The blue rectangulars are the single elements, and we can make, for instance, a subgroup consisting of 2 elements. It's fed by this microstrip line here and here, and here and here. Means we have here on the left side 4 such subgroups consisting of 2 elements combined with this line. Then the next plane of combination of the elements is this here. We close or we connect together or feed together these 2 subgroups with this line here and here. And the next plane is this one. We connect this subgroup, now consisting of 4 elements, with this line. Then we have, at this point, normally you can choose the center point here. In this case, we have an offset. Why, I will explain you. Again, normally you can here use this center point. Then you have a connection of a subgroup of 8 elements, and it's symmetrical installed here, and the same we can see here. Yeah, why we have here an offset means if you have an offset, then we have between this line and this line a common phase difference. And so this is, for instance, one possibility that the antenna is not directed perpendicular to this plane, means the main beam, it's not perpendicular localized if this is our rotation plane. This means we have a certain phase shift, and so the main beam is directed a little bit under an angle, let's say 10 degrees or so. We will discuss this in the next slides. And here we have the same number of elements. Also, the arrangement, it's in comparison with here, in principle, the same, but the connection is here made a little bit another. We have here the offset between the two groups, and here it's connected over, let's say, over this two lines. You can do it in this way, and to make the same phase difference between this line of elements and this line of elements, you can only use here a single offset. Means if you feed it here, all feeding points are center points, and only the main center point, it's not here in the middle, it has offset. If the center point is in the middle, the radiation goes perpendicular to this plane where the elements are arranged. So now we have, or let's have a little bit a deeper look what happens in case of such an microstrip antenna array. Here it's only shown the geometry of a Z-directed infinitesimal dipole. You know, infinitesimal dipole means in principle Hertzian dipole radiating into free space. We know this picture in principle, and we also know here this formula. This is the E field in the theta direction, means in this direction, and you know this here, the eta, it's our wave impedance in free space. You know it's 120 p ohm, this value. We also could write here Z0 means Z, capital Z, index 0. The wave number, this is the current on this first element as an Hertzian dipole multiplied by the length, dl, and this part of the formula you know already, and this determines the distribution of the E field strengths in a certain direction of, or regarding to the origin, means this is the angle of my observation point. We can choose R1 as in principle as a common R without index for amplitude or magnitude, or this difference with this set here. It's defined on the next slide, I think, in case of phase, if you want to compare or you want to add the phase. Yeah, all the elements now, in this case, Hertzian dipoles are arranged in a line, element 1 or Hertzian dipole 1, 2, n, large n, and so on. And now we look in a certain direction. Then we have to our observation in this. This is our wavefront, and from the origin, and it's the first element, and to the other elements, we have, let's say, different distances. It's clear, but if we look in a very, very large distance, then the difference between this radiation length makes no large difference. And we can see here how can we calculate the behavior to a field point in a very large distance, means in the distance r, or in and also under the angle theta and the angle phi. You know, we notice the angle phi, let's say it's for theta for elevation, and this it's the other direction. How can we calculate this now? If we look to the complete field strengths in our distance or observation point, we have only, or it's very similar, we only make a superposition. We add all the single field components of the dipoles, of the Hertz dipoles. Here you can see the sum. Then we can take out this term here. You notice it's coming from our dipole J, then it's our 120 p wave impedance, and then here we have the current distributions multiplied. The length is also here kept out, and we have only here the currents and here the angles of our current distribution. Yeah, because the distance observation point is very far away from our array, we can apply this as a general R for amplitude, and here we have to consider the difference between the distance and the single field points. And so we can make the following conclusion. We want to know what happens if we have n Hertz dipoles arranged in a certain distance to each other along a line, let's say along the z-axis. And what can we expect at a certain observation point very far away from this line of Hertz dipoles? It's clear that we are talking about a far field. And so we can say, we look to this formula, and then we have this part describes the element pattern of the single element. This is our single element, namely our Hertz dipole. And what we find here, in this bracket, the sum of this currents together with this angle function, this is called our array factor. In other words, if we want to calculate the behavior of a certain arrangement of single elements arranged in an array, in this case it's very simple, it's let's say along the z-axis, along a certain line with a certain distance, then the array pattern or the gain we can calculate by the knowledge of the behavior of the single element or the element pattern multiplied by the array factor. And it should be clear this multiplication in this case must be complex. The element can be arranged to form a linear, as two-dimensional or a three-dimensional array. The type, the size, and the position of the single elements can be arbitrary, but all the elements for this formula must be identical and equi-oriented, means the elements to each other cannot have, let's say, another polarization orientation. Then you cannot apply this, let's say, base formula. And here, this is what we have developed here. The two-element array consists of, in our case, of the single element description like here, and here we have in the rectangular bracket, in the brackets, the current by this angle function. It's the same like here. This is an example what happens if we make, for instance, or if we change the distance between two elements, we have an array with only two elements. Here, our Hertzsche dipole is the element pattern. We know this. And here we have the array factor. We have only two elements with the same current distribution. Here, the current at the origin, and here this is the distance. The two currents are in phase with each other, means this angle alpha, it's 0. If we change the excitation phase between the elements, then it's clear that we have also another behavior. Then we have not only the influence of the distance between the elements, then we also have the influence of the phase difference between the excitations of the two dipoles. Then we have another behavior of the rotation diagram or of our pattern. And this with the phase difference at 0 between the excitation currents is clear. Then our array factor, named here by AF, it's only this formula. You can see it here, and this is 0. Yeah, what happens if the distance between the Hertzian dipoles is a force wavelength only? Then we have a little bit. This looks like a little bit gain-like. It's not completely round. Then, if we increase the distance between the two dipoles of a half wavelength, then you can see here we have here a first 0. Here we have no 0. Then we have here a first 0 along this line, and it's clear it must have a certain gain. It must be a gain larger than the gain of a Hertzian dipole. You know the value. About 1.8 dBi. And here, if we make the distance a little bit larger, then we can see here that the diagram shows an ambiguity. This is this here. And because it's a cut, you have imagined it's symmetrical. And we have a gain, but we have, and this is named, we generate additional grating lobes here. These lobes, the name grating lobe means the gain of this lobe, it's similar or it's identical with the gain of the main lobe here. It can be a little bit larger, but the gain here is, or the directivity is the same value like the main lobe or the main direction. And so if you have such an antenna, or an antenna array in this case, consisting of two elements with this distance of 0.55 lambda or 0.6 lambda, for instance, then you generate a so-called grating lobe, which makes the pattern of this antenna, of this two-element array, not ambiguity. Yeah, here we have a short summary. The planar array antenna, the aperture size is sufficiently larger than the wavelength. Is clear because we want to have a higher gain. We want to have a better directivity. This is, let's say, the base why we build an array of antenna, why we build an array of n elements to increase the directivity. One method was to increase the directivity, the Yagi-Uda antenna. We have discussed it. Another possibility is to use larger reflectors, let's say parabolic reflectors or dishes or whatever. Then we can use antennas with, let's say, single element antennas with in form of a horn antenna. But here in this case, we have elements, for instance, consisting of patches, of microstrip patches, but the patch itself has about, I showed you, up with air as a substrate up to, let's say, 9 dBi single element. But if we want to achieve much higher gains, then we have to use the principle of, in this case, microstrip antenna arrays, means area. Now, the directivity of a planar array can written in this way. For instance, this is the directivity of the planar array. It's about the directivity of the single element multiplied by the number of n of the elements, and this is here the let's say, the angle of observation. If you look perpendicular, it's clear the cosine it's 90 degree, or if the cosine it's 0 degree from the normal direction, then it's 1, and if we go in the plane, means the cosine it's 90 degree, then we have the 0. Okay, this is the roughly the directivity of the single element. You can see here 4p, the area of the element divided by the square of the wavelengths. I explained it already. Theta 0, it's the main beam angle. It's clear. Then it's the directivity of the single element. Also clear. This is the area or the efficient aperture size of the single element. From our lecture, let's say of the second or third lecture, we know how we can calculate the efficient aperture size from an element or from, And now, with this number of elements, what we have discussed in the slides before, 16 elements, may be ranged as a 2 by 8 element or by 4 by 4 microstrip antenna array. Then we can say how large is the gain regarding to the single element, means the gain must be 16 times higher than the gain of a single element. At observation angle of 0 degree means it's a, we say, bore side or observation angle in the main direction. What does it mean? 16 times higher means if we know the gain of the single element, then the gain of the array, it's the gain of the single element, in this case, plus 12 dB. Why 12 dB? You make the logarithm of 16, and then you will find it's 12 dB. 2 means 3 dB, and 2 exponent 4 means 4 times 3 dB. 4 times 3 dB is 12 dB. And if you have to give the gain is given in dBi, means in reference to the isotropic radiator. And if the gain is given in, let's say, in our case of 6 dBi, then the gain of the array it's 6 dBi plus 12 means 18 dBi. This is the gain of the array consisting of 16 elements with a gain of a single element of 6 dBi, only as an example. Now let's look to the amplitude distribution yielding the side lobe or yielding low side lobe. The first side lobe level of such a linear array antenna and with a rectangular aperture, it's about 13.3 dB regarding the main lobe. This is on a side lobe level. And in case of circular aperture array, then this value, it's smaller, it's interesting, it's only about 17.6 dB. Yeah. If we have a rectangular or a square arranged array, then we have this value here. And if we have the array, it's in a circular shape, then we can reduce it by about a little bit more than 4 dB to this value here. This is very interesting. And for instance, radar applications, we want to have lower side lobe levels in comparison with these two values. But here again, we have here the situation that in case of 13.3 dB, that all single elements are excited with the same magnitude. And in case of a dish or of a reflector, this has it's not possible, as I mentioned before, to make the amplitude distribution in such a way that over the reflector dish or reflector plate, or you have at the edges the same magnitude like in the middle. It's impossible. But in our case of single excited elements, you can let's say in the borders of this array, you can realize this in such a way that every element, doesn't matter if it's in the middle or on the edges, can be excited with the same level. And this leads to this effect that the side lobe levels are very high. We will see it in one of the next slides. To reduce the side lobe levels, you can apply a certain distribution. Here it's given by either Chebyshev, or this is a combination of both Chebyshev distribution. It's not my it's not my goal or my direction to explain this now in detail. I only want to show you, if you make a magnitude distribution of an array consisting here of 3 elements, you can see that you can you can see that you have to excite the single elements with very different magnitudes. And then you can achieve, in this case, side lobe levels of minus 30 dB. Here we have a practical example. This array of square patch elements consists of 8 by 8 patches. And now let's look to the 3D pattern of this antenna. You see it here in the middle. All elements are fed, let's say, by the same magnitude and by the same phase. Means between the elements we have no phase difference. The phase differences between elements are 0 degree. And now you look here to this graph, or to this Cartesian readout, and now we find this is our main lobe, it's the main direction, and then this is our first side lobe level, and more or less exactly we have this distance of 30 dB, because all elements are excited with the same magnitude. This is what I want to say. And if we want to reduce the side lobe level, then we have to realize, I switch back, that the elements are fed with very different levels. These are the elements here at this position, source position. It's the source position. It's normalized to the dimension of the array. It's clear. In case of the square array, what we can see here, then in both directions we have the same behavior. If we have a rectangular array, then this normalization, it's only valid for width direction or for the length direction is clear. But you can see in the middle, the elements in the middle of this array has a high magnitude, and the elements going outside, going to the edge, like here, from the middle going to the edge. This elements here along the edge has the lowest magnitude in comparison with the center elements. Means the center elements have the magnitude 1 relative normalized, and the elements at in the near of the edges, all the outer elements has 0. Let's say 0.3 or 4 times the magnitude level of the center elements. And with this exciting of the elements, you can achieve about, let's say, 30 dB side lobe level. But you have to pay this. You have to pay this with a reduced gain. This is what I want, or what I have to say to you. But in our case here, let's say the direction of excitation is directed in another way. Means here I want to show you with such a patch antenna. You remember this example for the single elements working at about 29.5. I said all the time 30, about 30 gigahertz. We have here 28 gigahertz. It's in principle the same. You see here the dimension of such a patch consisting of 64 elements. Look here, is 52.2 by 52.2 millimeters in square. Yes, it's very small, and also the elements here has in principle the same dimensions what I mentioned in case of my example regarding the thickness of the substrate. What is the influence of the thickness of the substrate? This is also manufactured, I think, in LTCC, very small. And now we can also determine in principle that the area factor, if we assume that a single element has about, let's say, 6.5 dBi, then you can calculate the logarithm of this value. 8 by 8 means 64. And we have to realize the logarithm. Then you can see what happens. Okay. 8 by 8, 64 means 2 exponent 4, 16, 2 exponent 5, it's and 2 exponent 6. 2 exponent 6 means 3 dB multiplied by 6, it's 18, plus the gain of the single element 6, it's about 24. The gain should be about 24, 25 dBi. Maybe we can see it later. It's not given here. So what I want to explain to you in this case, not to realize, let's say, different magnitude distribution to achieve very low side lobe level. In this case, we want to achieve a steering and pure electrical steering of this antenna array. Means this main beam should be steered in this or in this direction. And how can we achieve this? And this is shown here. For instance, these patches are now fed with the same magnitude, but are fed with different phase angles from element to element. Here it's given as a, let's say, as the reference element in the lower left corner of the area. Let's say this is the reference element here, lower left corner. This element, it's driven with, let's say, with a reference angle, and the angle of the driving current regarding this element here and this element are different. It's not 0 degree, it's, let's say 20 degree in both directions. Then from this element to the over next element, it's, let's say, 40 degree, 60, 80, and so on. And to determine this phase angle for the driving currents, it's given here in this formula. This is the phase shift for the element N located in the Xn and Yn direction. We have here an element, let's say, if this is the element 1, then we can say here, this is our Y direction, this is the X direction, and you can name it, for instance, element 4, or element, this is the element, the first index is the X direction, then the Y direction. And then this is the element, for instance, 3, 2, or let's say here this element, it's the element 3, 8, first X, then Y, element 3, 8, and so on. Also, you have a matrix, then you can determine the phase angles also from the single elements which are located here in this array to drive or to realize only for this single phase difference. Then you can calculate, you can realize this steered angle. Then you can see here it's looking not perpendicular or to the normal vector of the array, it looks under a certain angle. And here the phase angle is changed for each element, driving for each element with this formula. The phase angles are different from steering angle to steering angle. And if you have chosen, let's say, 1, 2, 3, 4, 5 different driving angles of the elements, you can steer the antenna from this position. Looks on the bore side, it looks direct in the main direction, and then it looks, this here is the next angle of steering, next angle, next angle, next angle, next angle. And if you can realize this, let's say with a digital phase shifter, then you can, for instance, make such a steering in steps of or in increments of 10 degree. So the antenna looks bloop, bloop, bloop in this 10 degree increments. But you can make it also full analog, so that the steering is in the degree range. But it should be clear that the electronic behind this array, it's more or less very complicated, because you have to ensure that each of these elements follows this formula. And then in practice, you have, for instance, here to use memories in which all this, let's say, the formula is developed for this steering range. Again, if you did not take into account the magnitude distribution of such an array, then the steering angle of electronic steering mechanism, it's limited. Let's say the higher the number of elements, the smaller is the angle range of this electronic steering possibility. Then you can steer this antenna only in an angle range of, let's say, 10 degree or maybe 50 degree, 15 degree. It's very, very small because of the high number of elements. The smaller the number of elements, then the more you can steer this array. But the smaller the number of elements, the lower is the sense, or it makes lower sense to apply such steering mechanism. It makes only sense if you have a high gain antenna and to look to a certain direction with a very high gain. Okay, this is the problem of antenna arrays, in this case based on a single microstrip element, or in this case based on an array of microstrip elements. Here I go very fast through this slides because it's a special application. This was an antenna developed in our department, in our lab, for purposes of localization. And the antenna here, it's a dual frequency element. We can only assume, let's say let's assume it's a patch, a single patch element without the slots. The slots and this T-like structures makes the single patch working for two frequencies. But the principle, what I want to explain, is only valid for one frequency. We have here an array of 4 patches, and here you have a network. It looks very complicated, and because it's for 2 frequencies, and this network makes the following: you can feed all these 4 elements in such a way that you can achieve, let's say, for this array in parallel, depends on the feeding, you can achieve, this is shown here, 1, 2, 3, 4 different patterns in parallel. Means the antenna has at least, I switch back, the antenna has at least 4 different feed points, but not the antenna itself. This is the array consisting of these 4 elements, and each element it's fed by this network, and this network, which feeds the single elements, has also one. Wait, let's start here with 1. Here it's antenna 1. This goes to the antenna 1, and this goes to the antenna 3, antenna 1, antenna 2, antenna 3, and here's the antenna 4. Okay, this are for the antenna feed points, but we need also 4 different feed points for our, let's say, receiver, and this is shown here. Here it's a feed 1. Let's look around. Feed 2, feed 1, feed 2, feed 3, and here it's feed 4. If we use this different 4 feeds, every feed shows from this array a different pattern, a different radiation diagram. Again, this is shown here. Let's say this is for this diagram of the array. It's realized with, if we look, or if we excite the antenna over the feed 1, is this one. Then if we use the feed 2, if we excite the antenna over the feed 2, we have this radiation diagram. Then we excite the antenna array with the feed 3, then we have this radiation diagram. You can see here the difference is only that both diagrams are, let's say, has a direction of 40 degrees or more or less perpendicular to each other. And this is the last radiation pattern. It makes the difference of all these diagrams, and normally it should be 0. We have named it P mode, And this is the force diagram on the feed 4. So, and we have 4 different, let's say, radiation diagrams, but we have 4 identical patch antennas. And this is the interesting fact that you can have only one. Sorry, you can. This is let's say the base of the, or was the base of the antenna array. We have 4 identical elements, maybe dipoles, or in our case, square patches. But with the so-called feed network, we can achieve with this very small array 4 totally different radiation diagrams. And this is what I want to show you here. And the Y and the direction, or the base, why we have to realize these different radiation diagrams depends on a lot of things. Depends on the how to receive the navigation satellites, then the problems of distortions, visibility, and so on and so on. This could be realized with this 4 different radiation diagrams on a 2x2 or 4 element array, but with 4 different feed points. You can see this here in the compact visualization. Here the antenna, very thick, but not only this is what you can see here, the antenna itself. In the substrate between, we have this embedded this feeding network. You can see here the cross section of this substrate, of the compact substrate. You have not only this feeding network with hybrids here, you also have to realize left and right-handed circular polarization, and so on and so on. It was a little bit complicated. Okay, this was only an example. And now, this is before we come to the noise behavior of an antenna, we have to discuss about antenna measurements. It should be clear if you have realized an antenna, for instance, in such a case here, or in this case, we want to know what happens really in practice, how our antenna fulfills the demands what we have to, or what we had to realize. And then the measurement technique comes in the focus of our discussion. Now, let's start with the following pattern measurement idea. We have here our antenna, let's say, localized at origin. And now we have here our probe antenna for the measurement purposes. And now we can imagine, and this is the, let's say, the basic idea, to move the probe antenna over the surface of our realized antenna, our measurement device, or in the literature you can find antenna under test. This is the AUT, not device under test, like DUT, it's AUT, antenna under test. And we are flying with our probe antenna, and this is important, with constant distance. We cannot, if we change the distance, then we make a very large mistake. We have to hold constant distance. We fly with a constant distance, and also this radius, or this distance, has to fulfill the far field conditions. Don't forget it. We have to fulfill during the measurement the so-called far field condition, or we have to move our probe antenna with a constant distance in the Fraunhofer region, far field. This we have to consider, otherwise the measurement results are not correct. So you can imagine you have an antenna with very large dimensions, and now we have to measure this antenna in all angles over a sphere or over the surface of a sphere. And you know, if you switch back, or if you go back to our far field condition, we have 2 times the largest dimension of the metallic parts, the largest distance divided by square of lambda. This must be, or this is the base, and the distance R must be much larger than this given formula. Then we have the far field condition or the Fraunhofer region. So, and if we have a very large antenna, then the distance, the far field distance, it's, let's say, relative expressed in wavelengths. It's not very large, but if the antenna is low frequency, the wavelengths it's very large. It's clear, and only from this point of view, if you calculate, for instance, the distance must be observation distance must be 3 wavelengths. Then, in case of a, let's say, of a antenna for 1 megahertz, then the distance it's maybe 1 kilometer or so. It's very fast. But on the other hand, if you have, for instance, very high frequency antennas, means very small wavelengths. Also, you can find if you use, for instance, a high gain antenna with a large dish, then you also can see from this far field formula that you also have to bridge very large distances. We will see this later on. But first, the practical aspect for the measurement scenario here. If you want to measure the antenna, let's say localize here at the origin of this measurement coordinate system, then you have to move a probe antenna with constant distance on the surface of a sphere. Yeah, how to do this? In practice, yeah, either it's very complicated. You have to at every measurement point, as long as you in the near of the surface of the Earth, it's not a problem. But if you have to put the probe antenna in the height higher and higher and higher to hold this distance, if the distance is, for instance, let's say 50 meters, then yeah, how you can come to this point? Yeah, nowadays you can use let's say a small drone and can try to assemble the probe antenna on a small drone, but then you have to control the drone in such a way that you can hold this constant distance from the antenna, and then you can fly from point to point. But I think it's not very practical, and it needs a lot of energy, and also the antenna and the measurement receiver must be on board of this drone. All the things are very complicated. And so let's go to the relative theory. We can make the following. We can exchange the movement between probe and the antenna under test. We can fix our probe on a fixed point here. Then the distance R is constant, it's clear. And now what we are doing is we're moving our antenna under test here in all directions. And then we have it. Then we can, from this measurement point, look to our antenna, and we can measure every point of our antenna under test here at this point. It's only, let's say, a relative an exchange of the coordinate system. And this is shown here. Here is our antenna excited by the generator. We hold the far field conditions, and here this is our test antenna, and the antenna under test. It's, as you can see here, it's moved, and so, but it's the same. You can also excite the test antenna here, and you can receive it here. You know, it's exchangeable. It makes no difference. But here we say this antenna is the illumination antenna of our test antenna, and the test antenna or antenna under test, it's moved against this source or illumination antenna. Here the same illumination antenna under test. Okay, here it's shown the, let's say, the exchange coordinate system. The pattern of the antenna is proportional to the terminal voltage is clear. This is the terminal voltage means in this case a received voltage. It's a function of the angular position of the antenna, and so we can record. We can make a record over all angles, over the theta angle and over the phi angle. Phi angle is azimuth, and the theta angle is the elevation. And over these angles, we can make a record of all these voltages, and then we can construct the complete 3D radiation behavior of our antenna under test. And so it's very simple to measure such an antenna. The only thing what we have to consider is if we have antennas with a larger reflector, high gain antennas, again, then to achieve the Fraunhofer region or the far field, we have to bridge large distances. If you are out of a building, if you are in the, let's say, on a measurement test area outside the nature, it's not a problem. But then you have a dependence on the weather. If it's raining or strong raining, then it's not possible to measure an antenna, because also the measurement equipment must be saved from rain or from wind and other things, or snowstorm or whatever. So it should be a wish to install such a measurement scenario in a building, in a room. Here you can see such an arrangement outside of a lab. It's on a test area. We have two towers, for instance. Both towers are normally realized of non-metallic material. Means we use material, for instance, plastic or from timber or such things. But it's clear in case of rain, then also the measurement scenario will be influenced negative. So, and this is applied in a lot of cases, especially in the past we used such towers. But as you can see here already, in this case we have, for instance, so-called ground reflections. We have here a specular point, which it's only one reflection point. You have a lot of such reflection points. You can go along this line and you can find a lot of reflection points with different intensities of the incoming or reflected signal. But this we will discuss in the next lecture. And now I can say only thank you for your attention. And we will proceed next Tuesday with this antenna measurement systems. Thank you for your attention again, and have a nice evening.
Goodbye.
Goodbye. I hope you could understand me more or less better than in the last lecture. Okay.
Bye.
Okay.